Hi, and welcome to Talking Tech. I'm your host, Alejandro Hoyos, and today we're going to be taking a close look at Lunar Lake NPU. With us, we have Senior PE, Darren Crews. Hey, Darren, how's it going?
Hey, good. How about you?
Doing well.
Good to see you.
For those who are joining us for the first time, why don't you let us know what do you do at Intel and what did you work on Lunar Lake?
So I've actually been at Intel for quite a while. It's coming upon 21 years or so now. So I've been in the NPU team for around 7 years. I'm working on NPU architecture. And in terms of Lunar Lake, what I work on, I would say architecture kind of spans like two ends of the project. So at the beginning of the project, usually we're working on, what hardware do we need based on the latest workload trends, so we can accelerate those workloads. And then as we get closer to production, then we get actual real workloads from customers and let's say the latest workloads in the market. And we go and try to optimize those. We work with customers and ISVs to try to integrate into their software stack.
When you're starting the architecture, you started planning like a lot of years before.
Yeah.
So, you guys have to have like a great vision of, how does the environment going to look in 3 years? How is that challenging? How it is?
Yeah, it's hard. Really no one can predict what's going to be there in 3 years. You just have to look at what's the trend happening today, read papers and figure out, what people are publishing. Actually a lot of the networks that are popular today actually came out, quite a few years ago. But the problem is they're not kind of popular. So you have to decide, here's a new network architecture, it looks promising, but it hasn't really kind of picked up. So should we optimize that or optimize for other networks that we see?
What have you seen lately? AI, it seems like it's all over the place. What are the most common workloads that you're seeing today?
Yeah, most of the workloads are around transformers. I would say those are the new workloads that we see. So large language models, basically all the generative AI stuff. So besides large language models, there's also models like Stable Diffusion. Those are image generators. While large language models get a lot of the hype around transformer models, that they actually have a lot of other use cases. Let's say like transcription, like speech to text. Mm-hmm. That's another transformer workload that uses the same base architecture as a large language model. There's just quite a large number of workloads around transformers. Really, transformers are kind of replacing a lot of the previous workloads that we saw using other methods like convolutional neural networks or recurrent neural networks, LSTM networks. So it's really kind of taking over a lot of the previous network architectures that we saw.
So that's kind of the latest iteration on how to solve for these new workloads, like using transformers.
Yeah. Mm-hmm.
Okay, so let's take a quick look at, I think you already told us so we have transformers and large language models. Can you tell us a bit more about what it is, a large language model? Because we've seen a lot of them today on different softwares.
Yeah. So a large language model is transformer architecture. Transformer actually has kind of two components to it. There's like an encoder part and a decoder part. Encoder can kind of be thought as like a classifier, and the decoder is like a generator. Mm-hmm. So you can use just the encoder part as kind of classification. You can use the encoder and decoder part as translation. So let's say you're doing like language to language translation, or if you're doing speech to text, so you get speech in and text out. That would be like encoder, decoder, or it can just be decoder only. So that's the generative part. So that's what large language models are using. So they're really kind of taking those decoders and just scaling them up to incredibly large size. Anywhere from a few billion parameters to hundreds of billions of parameters.
All right. So now let's go back to Lunar Lake and the neural processing unit, the NPU. I was looking through the different architectures in there, and I saw that this is called the NPU4, which to me I was really surprised because I thought it was the second one, because to me the first one was the one that we use in Meteor Lake. Yeah. But that's not the case. It tells us a little bit more why it's the number 4.
Yeah. Well, if we look at the whole history of the NPU, Intel acquired Movidius in 2016. They were working on products mostly for IoT, computer vision type of products. So it was like drones, security cameras, that kind of thing. And that was using like classical computer vision methods, but it was starting to move over to deep learning based methods. So in 2018, we had our first NPU1 that was released. At that point, it was called MyriadX. It was a discrete SoC. So we had a MyriadX in around 2018, and the follow-on was Keem Bay. That was also like a discrete SoC focused on IoT workloads, but we were starting to work towards client. Actually, almost 7 years ago, we took NPU1, Myriad X, and we started working with Microsoft to see what it would look like to integrate that into a PC. So we enabled like a new software stack, kind of a new programming model that we're using today through MCDM, that's the Microsoft Compute Driver model, and DirectML. So those are kind of the early days of things, but we're kind of building upon all those previous generations of work really around what does the hardware need to look like to support the PC ecosystem, and what does the software stack need to look like. For
Lunar Lake, for the NPU, what were kind of the major overarching goals that you guys had for it? Like, what do you want to achieve with it?
Well, I think a few things. So one thing is we have a very large increase in compute. So we're like over 4x the compute. So expecting that the amount of AI workloads was going to increase, we had a large amount of increase in compute. But really we want these workloads to be able to use them like all day. So we want to have good battery life, cool and quiet operation. So we wanted to make sure the efficiency was improved as well. So while we're having a huge increase in the amount of compute, we also want to have a good increase in efficiency so you can really use those use cases all day. So we have around 2x performance or efficiency increase as compared to Meteor Lake NPU 3.
And I guess we can dive a little bit more. How were these efficiencies achieved? I mean, you guys, I think you guys through increased frequency crowd, changes in microarchitecture. What do you guys end up doing?
Yeah, it's kind of a mix. I mean, we have a new node, so that helps. Also adjusting the VF curve so we can support, kind of higher frequency at the minimum voltage, then we can get better efficiency. We also do a lot of microarchitectural improvements. Usually for neural networks, the most common operation is like multiply accumulate. So that goes to our MAC array. So we put a lot of focus in, optimizing the, power efficiency of the MAC array. Also, minimizing data movement is another important thing. You want to, minimize the time, the amount of times you're like reading and writing data, because that can also consume a lot of power.
Right. So you were talking about moving data, and I saw that in the new architecture, you guys have, like in Meteor Lake, we have a scratch pad. Oh, yeah. Let's start with that. What is a scratch pad within the NPU?
Yeah. So we have a software managed cache. As opposed to like a hardware managed cache where let's say it would manage, let's say if you have a cache miss, it would bring in the data, or if you run out of space, it'll evict the data. But in this case, we actually manage that by our compiler. So one thing about a neural network is like the execution is pretty much totally known ahead of time. So you can kind of pre-plan, optimally pre-plan all the data movement ahead of time. So we have a DMA engine. The compiler controls the DMA engine to bring in data at the optimal time, move data back to DDR at the optimal time. So let's say all the network parameters that we need to compute on, we'll bring in those, the weights, intermediate computation of activations will be kept in there. So that really kind of minimizes the amount of times we need to read and write from DDR. Like reading and writing from DDR is expensive from a power perspective. So in the spirit of kind of like keeping data local and saving power, that's kind of the optimal way, to kind of orchestrate all the data movement.
Right, because Lunar Lake, it's kind of designed towards mobile, so to a laptop, we want to conserve battery power, and therefore the scratch pad is you have the very quick access to the data that you need, and also you reduce the amount of traffic for the DDR and the power, because like you said, it's a pretty big power hit when you have to go back and forward and send that information.
Yeah, right. Yeah, I mean, it's like, 10 or 20 times or maybe more like power efficient to read out of the scratch pad SRAM than the DDR. So if you're going to be reading it a bunch of times, the data a bunch of times, you want to be reading it out of there. Also, we have higher bandwidth to the scratch pad than DDR as well.
Yeah, you said DMA. What is DMA?
It's just a copy engine. So it's just an engine that we use to copy data back and forth between DDR and the scratch pad, pretty simply speaking.
And that's the one that you guys, compared to Meteor Lake, you double in size.
Yeah, so in Meteor Lake, we had like 64 byte per cycle interface to DDR. So roughly you could say, 60 or so gigabytes per second. But DDR, if you have two channel, you can get over 100 gigabytes per second. So we weren't able to fully consume the bandwidth. But seeing that there's a lot of workloads that are bandwidth bound, certainly large language models can be very bandwidth bound after the first token. increasing or doubling the size of that interface to 128 bytes per cycle, we're able to fully consume the bandwidth out of DDR.
What is the first token?
Yeah, so if you're doing a large language model, let's say you're doing like a chatbot, you're going to enter a prompt, and let's say you enter like 100 words or something like that. You're going to go through the large language model, and you're going to do compute on all of those first 100 words that you've put in. Those can actually be, it's a compute-bound workload because you're doing compute on all 100 words that you put in. Now, like large language models are very large in terms of the amount of parameters or weights. Let's just take something that would fit on a client, let's say like a Llama model that's 7 billion parameters. So every time you do an inference, you have to read all those parameters in. But for the first token, you have a lot of compute too, so you have a lot of tokens you have to compute on. So you're actually going to be compute limited more than bandwidth limited. But once you get to the second token, you actually cache a lot of that information that you've computed. And you're only going to have one new token input, which is the last token that you just generated. That's going to like be output, and it's going to loop around as the new input. So all the parameters we actually have to read again. So those 7 billion parameters, which could be, let's say, 4 gigabytes of data, we have to read in just to compute that single token. So we move from like a compute-bound regime for the first token to a bandwidth-bound regime for after the first token.
And because you have to iterate and you have to keep loading all those parameters, that's why it goes from a compute bound to completely more of a memory bound. Right. And that's why having a scratch pad or increasing the direct memory access, it definitely improves.
Yeah, I mean the scratch pad doesn't help because our scratch pad is like a few megabytes, and it's like a few gigabytes of parameters, so you have to basically reread them every time. So
okay, that's good. Thank you. Let's talk about because you guys incremented the overall architecture. So you incremented the amount of neural core engines.
Yeah.
So tell me a little bit more about that.
Yeah, I mean, simply to kind of get more compute capability, you can kind of increase the frequency or increase the number of compute units, and we basically did both. So we have around 40% increase in the clock speed, and then we also triple the number of neural compute engines that we have. So for overall, it's like over 4x, slightly over 4x in terms of total compute capability.
So that means that in Meteor Lake we had 2, and now we have 6?
Yeah, 2 neural compute engines in Meteor Lake. Each engine does like 2K max of compute or 2048 max of compute per cycle. So we kind of kept that same architecture and just increased that by 3x. So we go from like around 4K max per cycle to around 12K max per cycle.
That's a pretty good improvement.
Yeah.
Okay, so on Lunar Lake, we have 6 more neural core engines, and that means that we have increased the TOPS. So we have gone from 11.5 to 48.
Yeah, right.
For those who's still learning about AI, what is TOPS? How does it define? What is it?
Yeah, I mean, TOPS is a little bit of a kind of a narrow focus figure of merit, let's say, for an NPU. What it stands for is trillions of operations per second, so it's 10 to the 12 operations per second. So it's a pretty huge number. When we're talking about TOPS, we're focusing on like multiply accumulate. So we have a MAC array. The MAC array does multiply accumulate, and we say those are matrix operations. Pretty much all, let's say like 90 to 95% of the operations are matrix operations. What that translates into is matrix multiplication or convolution. So that's pretty much most of the operations that are done, or 95% of the operations that are done. So the way we compute TOPS is it's how many matrix multiplication convolution operations that we can do per second. So on Meteor Lake, for an example, we had each neural compute engine could do like 2048 max per cycle. We have 2 of those, so it's 4096 max per cycle. And then an operation is either a multiply or an accumulate. So like a MAC is actually 2 operations. So we basically multiply like 2 operations times our max per cycle times the frequency we can run at. So if we kind of calculate all that out, then we get 11.5 peak TOPS. So if we think about, okay, how does that translate into a neural network? We can take like ResNet 50, for example. ResNet 50 has around 8 million, requires about 8 million operations to complete. So, and that's basically just the multiply accumulate operations through doing convolution. So we can think about what's the theoretical maximum performance that we can deliver. Let's say if we had Meteor Lake at 11.5 tops, and then we have ResNet 50 that's like 8 million operations. We can probably do like a little over 1,000 frames per second, kind of theoretically. And then maybe just to give like a counter example, like large language models, if we're doing like Llama 7 billion, and the amount of compute is actually dependent on the input token size or the number of input tokens. I was saying it's very compute bound. If we do, let's say 2,000 input tokens, I think our amount of compute is around 30 tops of compute. So I was saying ResNet 50 was like 8 million operations. And then if we look at like Llama first token, it's like, a million times larger.
Yeah, orders of magnitude.
It's just huge. So large language models, take a significant amount of compute. So we really need, those additional tops to be able to service those kind of workloads.
So about tops, is that a good kind of representation of the actual workload or the performance of the workload or the efficiency of the workload?
It's definitely a good metric. You can never go above, the performance you can deliver based on those tops, but you can definitely go below that. So if we look at transformers, there's two things. We see that some can be very bandwidth bound. Like I was talking, after the first token, if we're doing a large language model, we need a lot of bandwidth. So actually our tops don't help us a lot. What really helps is bandwidth. Like we need bandwidth. So that's one factor that's important. Another factor is the non-multiply accumulate operations. I would call those like vector operations. So in transformers, there's an operation like called softmax, for example, and it's part of attention scoring. So, the first transformer paper is called Attention is All You Need. It's about how large language models essentially use attention to figure out what the context is. And there's a softmax operation that's part of that. And that's not a multiply accumulate operation. It's a little bit different. So you really need good performance on that. A MAC array, like a matrix multiply, array, is not going to help you compute that. If you don't have enough of that kind of compute, you're really going to slow down the processing. And so one of the things that we did in Lunar Lake and NPU4 is we increased our vector compute by 4x. Over what we had. That's on top of the 3x. We had 3 times the neural compute engines. We have kind of 4x the vector compute. So it's like 12x per cycle improvement in compute from a vector perspective. And what we see is a lot of workloads, we can get significantly better performance. For example, Stable Diffusion uses attention layer. And on Meteor Lake, we're very limited in terms of actually that softmax calculation. But on Lunar Lake, we have a significant improvement in performance of that calculation, which helps us accelerate the overall workload more.
So that means like the tops is kind of like I guess we talked earlier, it's mostly based on the multiply accumulate for the matrix, but that doesn't take account the attention layer that we need, which actually, like you said, it gives context to the word when you're doing, when you're trying to figure out what was the input, which was like a type. Let's say the bird is blue or something like that. Yeah, we can have like 2 figure of merit, that we look at. The one figure of merit is the top, the peak tops, which is just based on, your multiply accumulate. And then we also have like effective tops. It's like how well can you use those peak tops? So we're always trying to improve, both the peak tops, which is, we can add more multipliers, we can increase the frequency, but then also effective tops where we're trying to improve accelerate other portions of the network that are keeping us from achieving our peak tops, which could be more vector compute, it could be more bandwidth, et cetera, or maybe more specialized kind of operations. No, okay, that makes sense. So we're talking about attention, the attention, I guess there's an attention block within the whole architecture, but there's also another block that we have done a lot of improvements, which is the DSP block. Let's start with what does DSP mean, and then what's kind of the function within the NPU.
Just to clarify, the attention block is a part of the transformer architecture.
Oh, okay, thank you.
Yeah, so we actually made the DSP improvements to help us on the attention block. So if we look at the history of Movidius, actually the DSP is as part of the core IP that they developed. It's called SHAVE, that stands for Streaming Hybrid Architecture Vector Engine. It's basically a vector engine. It's our vector compute engine. So what we did is we had a 128-bit width for the vector engine. What that means is if we're computing in FP16, we can do 8 FP16 operations every cycle. It's like 8 times 16 is 128. We can also do like 4 FP32 operations every cycle. So what we did is we increased the vector width, or like how many vector operations that we could do per cycle. We increased that from 128-bit to 512-bit. So we can do 32 FP16 operations every cycle, or 16 FP32 operations every cycle.
That's a big improvement from what we had before.
Yeah.
All right, so this has been a great conversation. How about we summarize all the different changes that have been implemented into the NPU, so that we have like a nice conclusion, like changes and also how it translates to gains and performance.
Yeah. Okay. Yeah, I mean, I think I would summarize it in a few categories. So the first thing is, peak tops increase. So that's just, the raw increase in number of multiply accumulates, the number, multiply accumulates per cycle, and the frequency we can run at. So that just gives us kind of more compute. The second thing is, of course, efficiency. So that really goes to the MAC array. Most of our power is going to the MAC array. So improving, the efficiency of every time we do a multiply accumulate, we want that to be more efficient. The next thing is really the ratio of kind of vector compute to matrix compute. We found for especially transformer models, also, back in the day, like RNNs and LSTMs, there was more higher ratio of vector compute to matrix compute compared to like convolutional neural networks. So we wanted to increase our ratio of vector compute. So that's why we made the DSP 4x the vector links, essentially kind of increasing the ratio of vector compute to matrix compute by 4x. And the last thing is bandwidth. We have all these engines that can do a lot of compute, but we need to feed them. So we need to be able to fully saturate the DDR bandwidth so we can fully take advantage of what the platform's providing us in terms of bandwidth. So that's where we doubled the interface width for the DMA engine. So those are kind of like all the key ingredients to really accelerate today's modern workloads.
No, that's great. Darren, thank you so much. I learned a lot. As always, a pleasure, man.
All right, thanks.
Thank you.